So I kind of decided to do a bit of a different talk than a lot of the kind of standardized talks mining companies give. And so I'm actually not going to talk about any of our ore deposits at all. I'm going to talk about some publicly available data. And I wanted to do this because I wanted to explore how you can model things from given data sets. Because often we inherit data from the 1960s, 1970s, 1980s, things like that. And I just want to kind of go through how you use inherited data. I really want to thank Andrew Steiner for essentially the mapping work that he had done and also being able to talk about this project. So Andrew Steiner was a student that was working in a project up in Canada, and I'll leave it nameless, but you'll quickly figure out where it was. And his mapping was actually pretty phenomenal, and so I thought that would be a good case to discuss. And one of the reasons I chose this is being from Nevada, I wanted to choose a Carlin-style system, and but also coming to a talk here in Canada, I wanted to do a talk on a Canadian deposit. So, so this is one of the geological maps for this project, and with some photographs of the terrain. And you have a lot of folding, you have a lot of complexity, there's a lot of shear zones, faults, and things like that. And that's often very difficult to model. So I've found frequently as I look through models of in 43101s and other things that there's a disconnect between the observable geology and what's modeled. And that's something we need to move away from. We need to move into realistic modeling. And that's one of the big focuses from Nevada Gold Mines is we're the joint venture between Barrick and Newmont in Nevada. And we're the #3 producer of gold in the world. And if you take our production out of our parent companies, we're the #1 producer of gold in the world. So we have a new focus on essentially improving the realism of our models. And there's not an acceptance of poor models and, oh, they just have variance and we can't reconcile and that's okay. It's moving very much away from that. So. All right, so this is the map that I'm going to be using in most of this talk, and Andrew had built this map in 2017, and there was two maps. There was one with some structural data on it, and then one with the general geology. But first, I'm going to talk about concepts in modeling. So my son is 10 years old, and he wanted to know what I'm doing for my work and what geological modeling is, and rather than trying to explain it to him with a concept that he's never learned on something that he's never seen, I figured I'd take something that we all have seen every day, and probably many of you have eaten one of these today. So let's make a model of an apple, and pretty straightforward. We can make a stem, we can make the apple itself. This is, in many regards, how we can start a geological model. So we had a photograph, which is a 2D representation of something, which in this case, we have mapping, which is often a 2.5D representation of a surface. And depending on where you're at, it can be truly 2D. So you can go wrong if you don't have an understanding of what it is you're actually trying to model. Because we all know an apple doesn't look like that. It looks fine in cross-section view. So visualizing that is a critical step, right? And I think this is the biggest challenge when we have geological modelers who don't have field experience begin to get into modeling. And I've had a lot of young geos who say, I want to go right into modeling. And it's like, okay, you have to wear out a few pairs of field boots first so that you can understand what it is you're trying to model. And so with that said, modeling software is a tool that we use. So we can create realistic geometries, or we can create non-realistic geometries from the same data. And this is actually the model that my son made of a banana. So we're going to start with Andrew's map, draped on topography. And we're going to step through a few of the things I did here. So one of the changes I made to avoid getting in trouble with any Canadian regulators or anything else is I essentially took the drilling data set and I applied fictional geology to it. So I went through and looked at the geological map and I said, okay, I'm going to make this be the geology. So that way, this model I present is not based on someone else's resource data and we won't have any problems there. So First, we're going to create a lava lamp geology model. This is one of the most common ones I see, and I think it's one of the biggest criticisms that people level at Leapfrog is, oh, well, it makes these bubbles and it's unrealistic. And I always go back to, we're the geologists, not the software. So we're using a tool to accomplish an objective. So we can all pretty much agree that that shape's probably not valid. Even if we gussy it up and give it some 3D geometries and make it look like a model, it doesn't really match the mapping at all. So even though it's based on real, like the data from that area. So, done. But we're going to go and do a little bit different approach. So we're going to apply the geology to it rather than bubbleography. So very few things in geology look like spheres. Some things do, but we want to start with maybe a stratigraphy in this case. So here we've taken the drill data and we've made a stratigraphy out of it. And so, you know, it looks better. It's maybe a little bit more realistic. Turning into a geological model, you know, we get something that's a little closer. But how does it actually compare to the mapping? Not at all. So there's something else missing here. So maybe we should start with adding some structures, because this area has a lot of different structures, and those are going to do different things to our geology than just a plain stratigraphy. So in this case, I've digitized in a fault and try to honor the mapping data as much as possible. So where we have known data, we try to give a little bit more weight, and where we have inference, a little less weight. So now we can start making some realistic surfaces based on that honor the mapping. And so here's the first fault. And then if one's good, let's keep going from there. So then we add some more faults in and add some cross-cutting relationships that were observed from mapping. And now we can cut the stratigraphy by these modeled faults and see how it compares to mapping. It's a little closer. It's starting to look like the general correct forms, but it's still not great. So we're going to add something besides drill hole data. And this is one of the things that I think often models fall over with, is we'll have purely drilling-derived geology, but then we ignore all the mapping that goes on underground in the open pit, all the mapping that went on before it became a mine. And so let's start adding some of that in. So in this case, I've added in a bunch of polyline points and colored them so they match the geological map so we could kind of quality control things. And there's a lot of data there, but if someone has spent years mapping this, the least we can do is spend 6 hours digitizing their map. And so now let's see what we build from it. So it looks a little bit more realistic. And we've now included our lithology from the drilling and the lithology from the mapping and the faults from the mapping. So let's go through and there's still some flaws, and we'll investigate one of those. So this pink unit in the middle of the map, it's mapped as pinching out, but I don't have it modeled that way, which is an important difference. So if that were a good host rock for ore, what do we just do to our resource estimation? So instead of having a unit that we know to pinch out from mapping and drilling, we haven't observed that. So let's go back and we'll make a few changes so that we can follow this one unit and make it a little bit more realistic. So there we go. So now it's pretty much mapping the observed geology, and we can move on. So let's look at how it matches our mapping. And so if you pay attention to, we'll use this screen. If you pay attention to the unit contacts, we want to see if those are being honored at the edges of our map or our model, or if they're not. And that's an easy, quick check, but often the edges of our model is where we have the least data, we have the least consistency. So let's go through and cut a couple sections, and we'll step back and go to the Leapfrog lava lamp model. And I think we can all agree that this is not the way we want to see geological modeling being done. I don't think this is the way the Seequent folks would want to see their software being used, because any geologist can look at it and say, well, that's wrong. And we want to avoid that first pass 30 seconds to tell how wrong a model is. So we'll look at the stratigraphic model that we derived from the drilling, and it's starting to match the mapping a little bit better. You can see, there's a few contacts that match up fairly well, and then there's other ones that don't match at all. And that's a real issue that we run into in modeling, where there's areas where a unit context map that no one's drilled because that area is thought to be uneconomic, or maybe we don't own the property. And so then if we don't have the ability to include that in our drilling, then our model is going to be flawed if it can't use the data that we do have. So now we'll add the faulted model with the stratigraphy and just the drilling influence, and it's starting to get a little bit better. So we're starting to see some more contacts being honored, but there's still issues. So now we have the unfaulted stratigraphic model where we use the mapping contacts. And so now you can see that the contacts match pretty well, but there's some strange geometries in there. And again, it goes back to, can we observe those geometries in the field? And in this case, no, we can't. So we're going to go back, add in the faults, add in all the mapping. And now, when we compare this to the mapped bedding, our orientations look correct down in the model itself, and the geometries and the morphology looks like what we observe in the field. So this brings me to which one of these would you trust for doing a resource estimate on? So if we're making a multi-million-dollar or sometimes multi-billion-dollar decision to develop a mine, how many times have you seen a poorly constructed model be used for that? I mean, I know I've seen dozens, and people have done a decent effort of it, but they'll spend all this time to create cross-sections, and then their geological model doesn't match the cross-sections. So if we were going to plan a $1 million drill hole out here in the middle of nowhere with helicopter-supported drilling, which one of those models would you want to drill test? The one that's based on the bubbleography, or the one that's based on solid field data with mapping that you can refine from additional mapping when you have questions and you say, this doesn't make sense in my model, let me go out and collect some additional data to understand that area. So which one of these passes the smell test? I mean, if you were to go back through the models, I think everybody here could pretty much quickly dismiss several of them. And my main point, and I'm trying to catch up for everybody else, is don't let the software do the work. The geologist should do the work. The software is a tool. And in this case, I think I made that model in 2 days, and I was talking to the geologist who did a lot of the mapping, and he said it was one of the first models that matched the mapping that he had done, because it was so complex that a lot of other areas had given up on trying to model it. So they modeled individual parts of it for each individual aspect of the resource estimate. And I think that's a really important thing to look at the geology as a whole, and I think that's one of the big key takeaways is just we collect all of this data, let's use it. So with that, I guess we don't have time for questions.